Good afternoon, all. Uh, my name is Chiral, and as it was already an introduction was given, provided I am having a 20 plus years of experience in Cathodic protection industries. So today in these sessions, I will take you uh, on a subject called Role of Cathodic Protection in Pipeline Integrity Management System. So So the content of my presentation will be introduction to the pipeline asset integrity management, why pipeline asset integrity management is important. I will take you through what is corrosion, what is cathodic protection, just basics, and then role of cathodic protection in pipeline integrity management. And then I would be introducing you to a tool called external corrosion direct assessment and the four steps which we do in external corrosion direct assessment. So to start with, what is pipeline asset integrity management? Basically, this is a strategy to ensure the reliability, safety, and performance of the pipeline over the life cycles. Any asset integrity program is basically covers these four things. One is the reliability, another is safety, and the performance over the life cycles until the decommissioning of that pipelines. So how we will achieve this? This we will achieve through uh, monitoring, maintenance, and improving your pipeline systems and to prevent failures. So as seen in the screen, pipeline monitoring is what we do for pipeline monitoring, internal corrosion monitoring, cathodic protections. Then for pipeline surveys, we do intelligent pigging, inline inspections, then coating integrity surveys like CIPR, DCVG, and then quantitative risk assessment, conditions assessment, FFA, and remaining life assessment. So these are the things, these are the part of any asset integrity management for to work on that equipment, that particular equipment. So why pipeline asset integrity is important? Sorry. Yeah, pipeline integrity is important because of the seven factor. One is safety. Safety is prevent leaks, explosions, then environmental protections like reduce the risk of harmful spills, contaminations, safeguard the ecosystems and natural resources. To improve operational efficiency, cost savings, prevent costly repairs, emergencies, emergency shutdown, reduce operational inefficiencies, regulatory compliance like OISD, PNGREB in India, or NAS, AMPP now, or ISO standards, reputation management, and overall emergency preparedness. The asset integrity, for me, asset integrity program is important is to prevent any unwanted incident. So now you know for any asset integrity, when we talk about cathodic protection, so corrosion, cathodic protection is one of the corrosion prevention methods. So what is corrosion? Basically, corrosion is defined as a degradation of metal by chemical or electrochemical reactions with its environment. And as you all know, corrosion is a transformation process from metastable state to the most stable state, right? We put lots of energy into ore to create a metal. So metal will go to its most stable state by getting it corrode by itself, right? So, and the effect of corrosion, we all know, like product loss, downtime, in terms of pipeline leaks, repair can take several weeks. Then severe environmental effects. You are all aware about Gulf of Mexico oil spill of BP, which has taken lots of toll on BP reputations. Then cost of rebuilding structures, loss of trust, loss of lives. We are from Vadodara, so recently there was an explosion in IOCL refinery Vadodara, which took two valuables life. So we wanted to avoid this, and that is why any corrosion prevention or asset integrity management programs are important. Typically in industries, there are two major corrosion prevention methods are used. One is coating along with corrosion inhibitors. This will be typically used for internal corrosion prevention, and another is coating along with cathodic protections. These are used for external corrosion preventions, right? So here, basically, uh, so now what is cathodic protections? So cathodic protection is an electrochemical technique used to prevent the corrosion of metal surface by making it the cathode of an electrochemical cells. Metal loss occurs at the anode and no metal loss occurs at the cathode. Another point, very important point is cathodic protection is a method of corrosion control that can be applied to a buried and submerged metallic structures. So application is only for buried and submerged metallic structures, not on a structures which are open to air or which are not buried. Okay, and second important point is it is normally used in conjunction with coatings and can be considered as a secondary corrosion control technique. So you know coating is essential, which is a primary corrosion prevention method, and on top of coating, cathodic protections is applied for secondary preventions, which means you know when there is a coating period, cathodic protection will come into picture and it will protect your asset. So, in order to make you understand what is the electrochemical process here, you know, for any electrochemical process to occurs, it needs four parts. One is anode, as can be seen in the diagram. Uh, Another is cathode. Then electrolyte. This is deep into an electrolyte and a metallic path. Anode is connected to a cathode. So at anode, oxidation reaction takes place, and at cathode, reduction reaction takes place. An ionic electrolyte is an ionic solution capable of conducting electricity, right? And a conductor that facilitates the movements of electrode, that is the metallic path. Typically, cathodic protections are of two types. One is called galvanic cathodic protection, which uses sacrificial anode. Another is called impressed current cathodic protections, which require power source to drive the current. In our terms, we call it as transformer rectifier unit. So these are the typical diagram for cathodic protections. Our left-hand diagram shows a sacrificial anode connection connected, and reference electrode is there to measure the potential, structure to electrolyte potentials, we call it, uh, to, to measure the effectiveness of cathodic protections. The second figure on right hand side is again of a typical cathodic protection, but in this we have a power supply unit, and that is why it is called an impressed current cathodic protection system. The basic difference we will understand in the following slides. Just to have a small idea, types of sacrificial anodes, we like a magnesium anodes, aluminum anode, zinc anodes. We also have a ribbon anodes nowadays available in the market, right? These are some typical impressed current anodes. Just for your reference, most commonly used are MMO tubular anodes. Nowadays, MMO linear anodes is also widely used. Then canister anodes are also used, and then high silicon chromium anodes. These are some typical impressed current anodes available in market. So comparison of sacrificial anode cathodic protection system and impressed current. See, the basic difference between sacrificial and impressed current is two things. Sacrificial anode has its own energy to do the electrochemical reaction, while in impressed current, the anode requires an external current from transformer rectifier to to electrochemical reaction to take place, right? Since sacrificial anode has its own energy, there is a limitations. It has a limited design life. So, you know, for a smaller design period, you can use sacrificial anode. But if you want a longer design life, say, for example, 20 years, 25 years, 30 years, in some cases, 50 years, and in reinforcement concrete, up to 100 years also, design life can be is possible. But for those types of life, you have to use impressed current cathodic protection system. Now to come with the differences, like in as a sacrificial anode cathodic protections, we don't need external power sources, but For ICCP, we need an external power sources. In sacrificial anode, current adjustment will be limited since it has its own energy. Since we are providing an power externally, we can control the current in ICCP. In high resistivity environment, sacrificial anodes are not economical since there is a driving voltage related problems are there. But in ICCP, we can manage by providing higher voltage designs. Installations wise, sacrificial anode are always simple since it is a distributed type. But in ICCP, it's a complicated type installations are there. Interference due to the small gradient of sacrificial anodes. Uh, there may be an interference, but can be minimized. But in ICCP, you need to have an interference mitigation program. Most important, very dangerous interference in terms of cathodic protection and corrosion prevention. And maintenance wise, also in SSCP, it is a negligible. You install it and you can forget it also, it will work. But in ICCP, regular monitoring and maintenance is required. So, role of cathodic protection in pipeline asset integrity. Prevention of corrosion. Basically, first role is the prevention of corrosion. CP prevents the pipeline from corroding, which is the most common cause of pipeline failures. Extending pipeline service life with cathodic protections, you can easily cathodic protection can be designed with ICCP for a design life of 30 years, 35 years, and 40 years. And in some cases, you can extend that design life by 10 or 15 more years by providing additional anodes as well. Again, reducing maintenance cost. Initially, the cost of implementation of CP will be there, but if you see a long term cost like for 30 years and 40 years of design life, that is a very minimum cost. Uh, and the regulatory compliance. Nowadays, for any cross country or hydrocarbon pipeline, for them, for that hydro testing, the acceptance of hydro testing is only allowed with an application of cathodic protections. And this is as per OISD standard, which comes under Ministry of Petroleum uh, and Regulatory Boards. So cathodic protection is very important in terms of regulation safeguarding as well. So now, what types of pipeline integrity management programs are there? Basically, there are three types of integrity programs. They all are having a specific requirements. One is an external corrosion direct assessment (ECDA), which is for the external corrosion prevention. Another one is an internal corrosion direct assessment. Obviously, it is for internal corrosion prevention, means internal corrosion prevention of your pipeline, right? And third is SCCDA, stress corrosion cracking direct assessment. Another form of corrosion which is very, very difficult to detect and most common failure process in corrosion industries. So, what does external corrosion direct assessment means? ECDA is a commonly used acronym for external corrosion direct assessment. ECDA improves safety of pipelines through assessing and reducing the impact of external corrosion on pipeline integrity. Its primary purpose being to prevent future external corrosion. This process prevents corrosion defects proactively from growing to a size that may ultimately hamper a pipeline structure integrity by locating and addressing corrosion activity, fixing corrosion defects, and removing the cause of corrosion. So, what are the four steps of ECDA? One is the pre assessment, where you collect the historic data, design data, then indirect inspections, direct examinations, and post assessment. See, for any asset integrity management program, these four steps are very, very important when you are on an operational side of the any asset. Pre-assessment. Let me go to the process. This is the process. Like, say, for example, When ECTC process starts and pre-assessment, what you will do, you will collect the data related to pipe, construction related, soil and environment related, corrosion control and operational data. For indirect assessment, we can have the cathodic protections, we can check the functionalities of cathodic protections, we can do monitoring, maintenance, TR functionality checks, ground bed test. Then we have coating integrity surveys like CIPS, DCVG, CAT, ACVG, and then interference surveys like AC interference and DC interference surveys. Based on those surveys result, we can have a direct assessment in form of coating inspections. We can have soil sampling for its chemical analysis. We can do UT wall thickness measurements. We can even identify the peat depth, and we can have the corrosion rate measurements only. Based on that, we can do post assessment remaining life calculations. Then we can have a better monitoring and maintenance schedule. We can have a better or a shutdown prevention schedule also, in terms of improving the reliability and longevity of the pipeline. So now let's come back to step one, pre-assessment levels. So for any buried pipeline or a cross-country pipeline, what type of data are required? Basically, you wanted to know the material of construction, a diameter of that pipeline, wall thickness, year manufactures, type of the pipe, coating applied on it. You can even wanted to have a data related to construction related data, like here it is installed, any changes, modifications, construction practices, for uh, remaining life assessment, RLA, right? You need to have engineering assessment as well. Basically, what I mean to say, engineering assessment means you wanted to have a monitoring based on level 1, level 2, level 3 and level 4 safety also. Say for example, if there is a pipeline 10 years ago, if you have laid a pipeline in a rural area, but due to this population growth and change in locality, now it comes under the urban area. So the reality will get changed. Then you can have allocations of valve, clamp, IJ. Integrity of IJ is pretty much important, since cathodic protections, for applying cathodic protection, isolation is very much important. Otherwise the current intended to protect the pipeline will be drained somewhere else, and you won't get the protections. Again, depth of cover, the pipeline, is always buried, but sometimes it happens because of erosion of soil. The pipeline gets open, and when it comes into the presence of atmosphere, oxidation reactions can easily take place and corrosion process can start. So in underwater sections, river crossings, for subsea pipelines, the buriedness is critically important. Locations of river weights, anchors, proximity to other pipeline structures, HV transmission lines, rail crossings. Nowadays, HV transmission lines cause lots of problems in terms of AC and DC interference. From an HV transmission line, for HV transmission travel is having an earthing system, and regularly it is draining some electrical current which is coming on a pipeline, and pipeline is acting as a conductor taking that current. Imagine someone working on pipeline can get a shock due to that. So HV transmission is pretty much a critical area, and so the data related to HV transmission lines are very much important. Even if it is within the acceptable range, a continuous draining of current on a HV transmission, due to HV transmission travel on a pipeline, can damage its coating, and there can be an hydrogen induced corrosion can happen due to this, right? So again, very much important. Soil and environmental related data are again very important. Soil characteristics, Soil chemical analysis is very much important for the present. We need to check the presence of SRB, sulfate reducing bacteria. SRB can create lots and lots of problems in pipeline. Another thing is resistivity. You have to check the resistivity, the change in the topography, change in the land. There may be yellow soil, there may be black soil. So it has a different characteristic. Resistivity can change, so does the current or a voltage gradient can change. So soil and environmental related datas are very much important, even in terms like, say for example, due to the populations and in city growth, a rural pipeline can comes into the urban section and somebody would upon the right of way of your pipeline, and in case of failure it would be a catastrophe. So again, land use related data is pretty much important. Fourth pre-assessment documentation requirement is corrosion control. Corrosion control, what are the corrosion control methods implemented in the pipeline? What is the type of coating? What is the cathodic protection? What is the design life of cathodic protection? What are the parameters considered during the design? You can know by rectifier, its types, anodes, its types. There are several types of anode bed. On a cross country pipeline of 500 and 600 kilometers, you would have typically 15 to 20 CP stations, cathodic protection stations, each having and different type of anode beds like shallow vertical, shallow horizontal, or a deep well type. So you need to have that type of data. Locations of your CP stations, whether it is at every 15 kilometers, it is at 20 kilometers. Drain point test stations locations, very much important to know the reach of a CP systems. You know how much your CP system is getting reach, whether you are having an enough protection on the pipeline, very much important. So again, CP evaluation criteria, stray current sources, as discussed earlier, due to high tension lines or other, substations, or even HVDC for railway line crossings. Those can create lots and lots of stray currents. In terms of plant piping, other plant equipment, or a plant earthing system can cause lots of stray current problems. Taste point locations, again, very much important. This will help you take the regular monitoring of cathodic protection, performance related monitoring, then CP maintenance history. Then in case there was no CP, then you need to have that data. Coating type, as discussed, current demand, CP survey data, history. Nowadays, in survey, OISD and PNGRB is mandating that you need to have CIPS, means coating integrity survey, at every 5 years of design life. Fifth, very important again, operational data collection, pipe operating temperature, operating stress levels and fluctuation, monitoring programs. If you have, say for example, if you have coupons, if you have a leak identification systems, then patrolling on your right of way, very much importance. Repair history, ruptures, why it has happened, failure analysis in case there was a failure. Then, as I discussed earlier, evidence of microbiological influence corrosions, MIC. If soil chemical analysis is done correctly and you have identified a presence of sulfate reducing bacteria, you can design CP system in such a way that will help you prevent MIC. So type, frequency of third party damage. Sometimes you are doing good, but third party, they doesn't know, and they can damage your pipeline. So those data are equally important. Hydro test dates, the pressures, operating pressure, initial pressure, design pressures, current operating pressures, why it has changed, what are the reasons. This is again important. So if you have those sets of data, you can go to an indirect assessment level. Basically, for any pipeline asset integrity management program, indirect assessment is very much important, since the pipelines, as I told, cathodic protection is only applicable when a pipeline is buried or in a submerged condition. So, you cannot see your pipeline through your naked eye. Now imagine a pipeline is buried a 2 meter below the ground level. You will not know where the corrosion is happening, why corrosion is happening, and for what reason corrosion is happening. You have to rely on data, and this data you can only get it from an indirect assessment level by checking cathodic protections functionality check, or by doing coating integrity survey known as CIPS, or a DCVG survey. There are alternative coating integrity methods are also available in terms of CAT, which is current attenuation testing, and you can verify its coating. You can pin size the coating defect through ACVG, which is called alternate current voltage gradient. I am not discussing those two in these presentations due to time constraint, but we will take it on some other time. Another two important surveys are AC interference surveys and DC interference survey. Nowadays there are advanced technique where you can do a simulation designs of your AC and DC interference, stray current interference, and you can have a mitigation design. This also currently I am not covering. We will cover this thing in some other, as it requires lots of discussion and calibrations on that part. So, with this program, we will cover these three: cathodic protection functionality checks, CIPC, and DCVG surveys. So now, before going to a cathodic protection, design of CP system, why it is important. We need to have a proper planning and design of CP systems are crucial to pipeline protections. A good design will give you a life of 40 years. If the design is not correct, or if you have made some mistakes in your remoteness calculations or current attenuations calculations, then it may fail. Wrong selections of anode bed can also lead to a pre-designed failure. And the considerations, pipeline size, the environment, as I told, soil type, moistures, and geographical conditions. Sometimes, a pipeline engineer or a cathodic protection engineer will design a CP system for 40 years, but after 10 years in operations, the parameters will change in such a way that they have to redesign or recalibrate those things due to external factors. Lots of foreign pipelines will come, or foreign installations will come in the vicinity of a right of way, or it is crossing your pipelines, requiring a regular redesigning of your CP system. Again, installation, proper placement of sacrificial anode or impressed current electrodes, ensuring adequate power supply and easy access for monitoring. The placement of anode is very much important. Imagine there are two pipelines and your anode bed is in the vicinity of another pipeline which you are not protecting. It will impact that pipeline. So you need to have you need to use your mind, to select your anode bed locations. Anode bed locations should be a remote locations in terms of impressed current, and it should be a free of interference. Interference prone zone should be avoided. Monitoring and maintenance means regulars. Our OISD and 226, OISD standard 226, even NEST and AMPP standards, and your PNGREB mandates cathodic protections for regular monitorings. I will share these things along with the PPT afterwards. So various parameters, CP, like pipe to soil potentials, anode bed readings, anode operating procedures, TR functionalities shall be regularly monitored. Current and system performance you have to. Even you need to check on your test stations, AJBs, CJBs, etc. Data collections for decision making, continuous data of CP effectiveness helps in proactive asset management and maintenance planning, adjustment and optimization. You need to, due to some reason, if your cp is insufficient or the current has dropped or it is not reaching the midpoint intended attenuations, then you need to adjust the current based on the environmental factors like soil conditions, water salinity, or change in pipeline layout. So now, another critical indirect assessment is CIPS, which is close interval potential survey. This will identify coating defect zone. So, in this survey, as can be seen on a diagram, a person with the help of voltmeter, data logger, and with the help of copper wire, which he will connect to a test station will take the reading on the entire length of pipeline at every meter. So you will have, and that with the help of GPS satellite synchronization interrupter switch. So in this survey, you will get a potential data of every meter. This will help you identify whether the pipeline is protected or below protected or overprotected, and equally you can identify which are the area where uh, corrosion or coating defects are taking place. A graphical representations of CIPS survey reports. As you all are aware, for Catholic protections, acceptance criteria is minus 850 millivolts of potential, and on potential should be minus 1200 millivolts. So anything between minus 850 to minus 1.200 millivolt, 1200 millivolts would be in a protected region, and your off reading should be in that. So through these graphical representations, distance versus potentials, the red line you can see that this is all under protection level. In this diagram, you can see the overprotected area, the op potential going below about 1200 volt millivolt. Then these are the expected coating holiday areas. And now if you see carefully with this survey, sorry, with this survey you can from 39.150 to 39.30, which is almost 150 meter of holiday area is expected. So you cannot excavate entire 150, it's a costly method. So to pinpoint that, again, to pinpoint this area, you can do DCVG, which is called direct current voltage gradient, and you can pinpoint location with the help of GPS to an exact coating defect locations, which you can further which you can further have a direct assessment on that. You can repair that coating defect. So for identifying that exact location, another survey is carried out along the pipeline route, which is called DCVG. The full form is direct current voltage gradient survey. This is the equipment used for the DCVG survey. It's a simple analytical equipments where a person will connect two of the reference electrode. These are copper sulfate reference electrode, and will walk on those possible coating defect locations, that 150 meters which I talked earlier. So this is how it will work. A CP unit or interrupter will signal the generator, and when the person will walk on the coating defect, this is the better slide. When he will, uh, when he is approaching the defect locations, his needle will move. The voltmeter will to a right. When he is exactly on the top of the defect, his needle becomes straight and remain stationary. And when he would means he would walk away from the defect, 8 needles of the voltmeter will move on the left hand side. So this is how he can identify 150 meter to an exact per locations where there is a coating defect. Even you can identify multiple coating defect locations in that 150 meters. So this is how asset integrity or a coating integrity surveys are carried out, and then results analysis of a DCVG defect. If the gradient defect gradient is less than 15%, which indicates the average coating conditions. If it is between 15 to 35%, then indicates bad coating conditions, and greater than 35% indicate poor coating conditions. Now there are two photographs I am showing to you. The top one is for 15 to 35%, which is a bad coating, which during the direct examinations, direct assessment with dig verifications, we found it out. And greater than 35%, you can see the defect size, which is 0.2 meter by 2.37 meter of coating defect can be found with the help of this survey. So now during these types of survey, you can also collect an additional informations like distance measurement, photographic records, AC potentials, overview of the conditions of test facilities, and possible source of stray current. So now step 3, direct assessment. When you know where are the coating defects, what you do is you do an excavations at that coating defect locations, uh, and then that excavated coating you measure, as can be seen in your earlier photographs. You clean the pipelines, you measure the coating defect, you can measure your UT, you can plant your the penetrations, any corrosion happening or all. You can clean, and then you can repair it and back repair it with your coating repair, wrapping coating, and you can make it further. So coating repairs shall be carried out, UT measurement and MFL to know the extent of corrosion. You can even carry out magnetic flux leakage test to know the extent of corrosion. So this is typical, after repair pipelines, how it is been seen when we found the coating repair, what you do. So here idea is, when in our initial slide, I told cathodic protection is a secondary corrosion prevention method which works on tops of coating. So, during designs of cathodic protection are designed for the percentage of coating defect or coating factor, right? So it would be like my design would be a 10% of coating defect or 50% of the coating failure. So with this type of survey, when you find a coating, you repair it so that it will come back. Your coating integrity will come back to its original states, and you can have a design life. You can attend your design life, and thus you can increase the design of your system. Another thing is, based on the after completing this type of surveys, you can have a remaining life assessment as per ASTM 5G. You can have a maintenance schedule again based on your records. You can do corrosion rate measurements, etc. So this is the step for post assessment level. So this is what about the asset integrity. Now you can improve this asset integrity of pipeline with the help of cathodic protections by implementing a smart technologies. Nowadays, people are implementing it with real-time monitoring and data analysis. We call it remote monitoring, or a smart CP stations are also used. You can even develop more efficient CP system, cost effective, sustainable, with the help of at regular or your defect prone area. You can even install coupons, you can even install probes, and you can have a real time corrosion data can also be identified and can be taken based on corrosion coupon or a polarization coupon. And So these are the future trends. Even people have started, I mean, in industries, they have started implementing these types of installations as well. Now, conclusion: the cathodic protection is a crucial for preventing corrosion while ensuring pipeline integrity, extending asset lifespan, and reducing operational risk. Long-term benefits are help. It's a cost-effective, safe, and environmentally responsible pipeline operations. An integrated approach to asset integrity management, including CP, is essential for maintaining pipeline safety and reliability. At TCR, we have developed a very good software called Asset Integrity Optimization Management Software, which can help you comes with this all four datas of asset integrity. With this, I rest my presentations. Thank you for your attentions and any questions.